All right, happy Monday. This video is to help you guys start and get going on our practice questions. On the whiteboard, you can see that I've kind of set a goal for you for each day. About 10 to 11 questions per day is our goal now to Thursday. And if you can work ahead, that's even better. Actually, it's much better. But our job this week, our learning target is to review and practice the concepts that you have learned previously this year so that you can do the best you possibly can on our state testing, which is Wednesday and Thursday of this week. So let's begin. Alrighty, so our question number 1 is taking us back to seismic waves. And a couple of things to remember with these practice questions is you may not see a question just like these, but the information, the topics, the content will be what you are going to be tested on. So let's begin. Okay, so another tip, read everything carefully when you are taking the test. A lot of the times mistakes are made not because you don't understand the information, because you misread what the question was asking you. And sometimes there are clues in the questions and the answers, so take your time and do your best this Wednesday and Thursday. Okay. Composition of the Earth. How do we know that the Earth has layers? We've talked about that this year, and one way that we know that Earth has layers, and probably the most important way, is using seismic waves, P waves and S waves, which are also the waves that are responsible for earthquakes. They travel through the ground, and some travel through solid and liquids, and some waves travel only through solids. So here we go. Let's review. So it's reminding you that there are 2 basic types of seismic waves, S waves and P waves, and we use them to study the interior of the Earth. There are several clues for you to read, and then it asks you to select 4 statements that can be concluded from this information. So first one, S waves travel only through solids. Now this isn't true or false. This is all stuff that it's telling you that you are going to use. P waves at 30 kilometers depth change direction. P waves can travel through solids and liquids. S waves and P waves are detected from 5,200 kilometers to 6,300 kilometers deep. Okay, so if S waves and P waves are detected in those layers, then they must be a solid. Because remember, P waves can travel through solids and liquids. S waves travel only through solids. So P waves and S waves can be detected at that level. So that's basically like the core, because the composition of Earth from its surface to its center is 6,300 kilometers down. Alrighty, so I'm not going to read this to you word for word, but things to think about and put together. Alrighty, so you read these statements and then you have to select the 4 best choices. First one says, there is a change in density occurring at 30 kilometers. You want to check that one, because how do you know that there's a change in density at 30 kilometers? Because there's a change in direction of the P waves. That means that the density of the material that that wave is traveling through has changed. We'll see that, we'll talk about that more in the graph down below. There is a liquid layer from 2,900 kilometers to 5,200 kilometers. Well, if it's liquid, then there would be no S waves. And let's go look for these numbers up here. It says P waves but no S waves are detected from 2,900 to 5,200 kilometers deep. Looks like that's another conclusion that we can come up with. Awesome. The densest material is found from 2,900 to 5,200. We know that's not true because S waves cannot travel through that layer, P waves, but no S waves are detected at that depth, which means it's a liquid. And liquids generally, are less dense than solids. So that can't be it. Next, the densest material is found from 5,200 to 6,300. This one's a little bit of a stretch. This one is testing whether or not you remember that the deepest layer, the bottom layer, is the densest layer. The reason why we even have layers in our planet is because of density. The most dense part of our planet is our core, because it's the densest material, solid, iron, and nickel. And the least dense material is our crust, and that's why it's on the very outermost top layer. So that is why this one is also an answer. Okay, we need to pick one more. There is a boundary between solid and liquid layers at 30 kilometers. That's not true. We know density changes, but we have P waves and S waves traveling through that. So here we go. How do we know that? P waves, hold on a sec. There we go. S waves and P waves are detected from the surface to 2,900 kilometers. So that includes 30 kilometers deep. So there is no boundary. Sorry, lost track of my spot here. There is a boundary between solid and liquid layers. Nope, because P and S waves are traveling through layers until 2,900. So that can't be correct. Finally, guys, there is a density change that occurs at 2,900 and 5,200, and that is correct because we have P waves, but no S waves are detected. That means that there is going to be a density change because we have a phase of matter change. We have a liquid to a density, or to a solid, excuse me. So density is changing, and we see direction change. So this is a hard question, and this is a really hard question to start with. So if you're like, oh my gosh, I'm gonna fail this, don't worry. This was just a really hard question to start with. The information that you're being tested on is density and layers of the earth and seismic waves. P waves and S waves tell us that the layers of the earth have different densities, and we know this based on the wave's behavior. Okay, the next question might help you visualize this first question. All right, so let's take a look at it. Moving along. And I do recommend that you guys write down the notes and stuff that I have on my paper, because it's going to help you. It's going to help you remember this information as you review it. I'm going to move myself over there. There we go. All right, let's focus. There we go. All right. So this one is asking to circle the regions on the graph where seismic waves enter different layers. So we're dealing with density again. Okay, speed of the seismic waves is going to change as the layer's density changes. And that's what we're looking at here. This would be like a little click and drag. This is going to be interactive. So you would, you're being asked to draw or drag arrows where speed is changing, density is changing. So each region of the graph, click on each region of the graph where seismic waves entered different layers of Earth's interior. How do you know that seismic waves have entered different layers? If you said, because the speed changes, Mrs. Height Susan, you're right. The speed changes, the wave's speed changes when density changes. And that tells us that there are layers in our planet. So I wrote you a little note right here. Speed of wave changes when density of layer changes. Density indicates different layers. Okay. We use seismic waves to provide us with evidence. We're having trouble focusing, I think. Okay. So here is your graph. Let's break it down. You're going to see graphs, you're going to see diagrams, and you're going to have to interpret them. Read them carefully. take a look at the X and Y axes. Read the title so that you understand exactly what it's showing you. So this side, your Y, is speed. We got 0 to 10 to 15. This X-axis is depth. So we're at the surface at 0 to the center of our planet over 6,000 or 6,000. Okay, this is our core, this is the surface. Let's take a look at what this graph is doing. At 0, the seismic waves are increasing in speed, and then they decrease. And then they're increasing, but it's like increase, decrease, increase, decrease, increase, decrease, little bits. But it's still overall continuously increasing. And then it increases a whole lot, or not maybe a whole lot. It's not super steep, but it's still increasing, but it smooths out, which indicates maybe it's a uniform material. But then what happens between here and here? This is a massive slowdown. You are currently traveling at, let's see here, 9 kilometers per second. 9 kilometers per second. And it's like putting on the brakes. And at this particular point of our planet in this layer, we go from 9 seconds or kilometers per second to about 4 kilometers per second. That tells us there is a huge difference in density between this layer and this layer. Okay, I don't know if you guys remember this, but waves, energy, sound, etc. travels faster in more dense layers, like solids, and waves travel slower in less dense material. Solids tend to be very dense. Liquids tend to be less dense. So this is indication that we are going from solid to a liquid. Okay. We have speed picking up again as we travel through that layer. And then we have an increase as we travel into the solid core. Okay. So overall, these lights, they keep going on and off, sorry. Overall, this graph is showing us there are changes in speed of seismic waves, which tells us there are layers. And when speed changes, density is changing, which means we are going through a different layer. So select the 2 processes that occur at mid-ocean ridges. Oh, I'm sorry. Am I? Sorry. I moved on to the second question. I know they're really close together. My bad. The only thing you had to do on this question was put arrows where seismic waves enter different layers. So when you see a change in speed, you have entered a new layer. And if you put some arrows in those particular places, you were right. Okay. Now we can move on to number 3. Sorry, that was number 1 and number 2, and now we're ready for number 3. Number 3. All right. And if you guys have any questions about what we are going over right now, I will be back on Tuesday and we can go over them together. All right, number 3. We are leaving seismic waves behind, but we are still in earth science. There's going to be lots of earth science on this test. Number 3 says, select the 2 processes that occur at mid-ocean ridges. I love mid-ocean ridges. We spend a lot of time talking about them. This is where seafloor spreading happens. It's a divergent plate boundary. Iceland is the only place above sea level that you can be and see and walk along a mid-Atlantic or a mid-ocean ridge, which is the mid-Atlantic ridge. Otherwise, they're all in the bottom of the ocean. And they're responsible for lots of cool stuff. So 2 processes that occur at mid-ocean ridges. And the best answers are material rises from the mantle to the crust. So this is a place where new crust is being made. New crust is being made at these ridges and pushes out the old crust. And as you get away from the new crust, this mid-ocean ridge, the crust gets older and older and older. And we'll see that in a future problem here. Sediments from the crust sink into the mantle? No, not at a mid-ocean ridge. It's all about making new crust. Crustal rock subducts into the mantle? No, that's not at the mid-ocean ridge. I drew you guys a little picture up here. It's not in color, I'm sorry, let me explain it. This is my ocean. These are my continents. This is my oceanic crust. Due to convection, we have material rising from the mantle, rising above the crust, cooling, making new oceanic crust, and it's moving the crust outward. It's like a conveyor belt. Subduction is occurring here and here, where the oceanic crust hits the continental crust. And oceanic crust is more dense, so it goes under the continental crust, back into the mantle, like a big recycling center. Here is where new crust is being made at the mid-ocean ridge. And this, remember, is a divergent boundary. Divergent boundary, where the plates are moving apart from each other. So the only other process that is correct is thermal energy rises from the mantle to the crust. And remember, we talked a lot about that with lava lamps. We have these, and we did an experiment with candles and oil and pepper flakes to show convection. Energy is rising from our hot core. Hot things are less dense, so they rise, and as they cool, when they're farther away from the heat source, they become more dense and they sink. And it's just a constant cycle that we call convection. Okay, and this thermal energy rising is what brings the material to the surface of the crust at these mid-ocean ridges, and new crust is made. Okay. Last, tsunami waves transfer energy from the crust to the mantle? No, that doesn't even make sense. Okay, we'll talk about tsunamis later. Alrighty, what other notes did I give you guys here? Gave you guys a couple of notes if you want to jot them down. And remember that subduction, where oceanic crust is going back into the mantle, that only occurs at the continents and the oceanic crust, not mid-ocean ridges. That's where oceanic crust is just, plates are moving apart from one another. Okay, so that's 1, 2, and 3. That was a lot of information. If you need to take a break, take a break. Let's look at number 4. All right, number 4. Put some notes on there for you. We're still in density. There's a lot of questions about density. Density is a big part of the 8th grade curriculum and kind of understanding how things happen on our planet. All right, so this one is asking about your understanding of density again. So here we are with density, and it's not asking you for a definition, but remember, the more dense a material, the more stuff in a volume of space, the more dense it is. And the denser materials in our planet are at the bottom layers. That's the inner core. And the bottles that we made this year, the densest material was on the bottom, and we have layers because the density makes those layers. So this question is asking you to look at a chart and to complete a diagram, testing what you know about density. And you have 6 different elements. It's misleading. It's giving you atomic masses. They don't matter. Atomic mass does not matter. That is like a distractor. So you don't even have to look at atomic mass. What it's asking you is about density. So focus on what it's asking you. Move each element into the layer in which it would be found in the highest concentration after the planet differentiates into layers. Differentiate just means we have different layers that were formed. And why? Because of density. All right, it's all coming back. So I put a note here. Think density. Top layer is the least dense. The bottom layer is the most dense. Always, especially when we're talking about the formation of our planet's layers. So when you look at this chart, you notice right away that iron and nickel are the most dense. They're the highest numbers. So they go into the core of our planet. The less dense materials, silicon, sodium, calcium, and aluminum, they are less dense, they are not in our core. They are going to be somewhere in the outer layers. And that's it. This is showing this protoplanet means when our planet was really, really hot and we didn't have layers because things were all melted together, but as it cooled and materials solidified, they formed layers. So that's it. I hope that was feeling a little bit more familiar. And that was, don't let these words confuse you. It's just asking you about density. Most dense materials are going to be in the bottom layers, the center of our planet. Least dense materials are on the outer layers. Okay, we're going to go over number 5, and then I'm going to be done with video number 1. And you'll be halfway done with the goal for today, questions number 1 through 10. All right, let me adjust this a little bit. I wrote a lot. All right, we'll just do this. Okay, so this one is asking you to use the information on the diagram and your background knowledge about seafloor spreading. Seafloor spreading, divergent boundaries, new crust is made. Okay, and then it says explain 2 pieces of evidence that support the hypothesis of seafloor spreading. You are not going to be asked to do short answer questions on this test. This is an older question, and I think they did away with the short answer responses, but you can tell me if I am wrong. Okay, so this is a good review. You have the Mid-Atlantic Ridge. You have numbers that show approximate ages on either side. And if you look at that, they're pretty much the same. Okay, 50, 55, 80 is about here, 75 over there. But if you went over here, I bet it would be 80. So what this is showing you is the Mid-Atlantic Ridge. And the youngest rock is in the middle because that's where the magma is rising up, cooling, and the conveyor belt continues, making new ocean floor. Igneous rock, magma and mantle material, ocean sediment. Lots of information. This is what you need to know. At mid-ocean ridges, the youngest rock is in the middle, and we know that it's spreading because it's mirror image. You have the same age of rock on either side of that mid-ocean ridge, and you have the same, what we call striping. So the iron material in the rocks, when those rocks cooled, lined up to magnetic north. And what we see in the rocks is it isn't always lined up to today's magnetic north. Sometimes it looks like it's switching polarity, and it's the same on either side of that mid-ocean ridge. This evidence supports we have seafloor spreading. All right, I am going to try to show you what I wrote here. You can write it down. You can absolutely bet on being asked a question about seafloor spreading. Evidence that it exists, the youngest seafloor is at the mid-ocean ridge, right here. The seafloor age gets older as it goes from the mid-ocean ridge towards the opposite continents. Conveyor belt. Pause it if you need to. Number 3, the age of the seafloor is a mirror image on either side of the mid-ocean ridge. That's what those numbers represent, is the millions of years old of that rock. And finally, the magnetic striping is also a mirror image on both sides of the mid-ocean ridge. I'm repeating myself. I'm sorry. Okay. Fun fact, because you know I love fun facts. Earth is 4.6 billion years old. So BY means billion years. But scientists have found that the average oldest seafloor, which is along the continents, because that is where it's the oldest, because it's being pushed out, it's only about 200 million years old. Why? Because it's subducting underneath the continents and getting recycled. That's so cool. Awesome. Science, as Mr. Canterbury would say. Alrighty. So those are questions 1 through 5. I hope that was helpful. Keep going. Your goal for today, Monday, is to get questions 1 through 10 done. If you don't get 1 through 10 done, please work on it as homework, and you are always welcome to work on these as homework. We will review the material together in class. I will post a second video if I have time to go through questions 6 through 10. All right, do your best. You may talk and work with a neighbor, and stay focused.